let's start. Hello, everyone. Welcome to this Reason seminar. And it's my greatest pleasure to welcome Futsi Kom today. Futsi is a professor of software engineering at Polytechnique Montréal and Canada CIFAR AI chair on trustworthy machine learning software system, and an Arthur B. Donald Fellow and research chair on software quality assurance for machine learning application. I had the pleasure to know Futsi since around 2019, where he was organizing and initiating a series of seminars called Software Engineering for Machine Learning Applications, SEMLA. And it was, especially at that time, before software engineering for AI become like so mainstream and attract a lot of interest, it was very insightful, and the whole symposium, how it's run, it was very fresh and creative. So I encourage you actually to also watch it on YouTube and look at the presentation there. And it's kind of a testament of how Futsi is creative and initiates a lot of things in the area. So he is also a co-founder of Software Engineering for AI training program, and the principal investigator for Dependable Explainable Learning project, and also a co-founder of the Quebec's initiative on Trustworthy AI. So he's very active in the software engineering community, but he also kind of is able to unify that software engineering and AI. So I'm very much looking forward to his presentation on engineering trustworthy AI system. And yeah, so the floor is your parenthesis. So he is happy to take questions as we go. So that make a very interactive presentation. So welcome again, Futsi, and the floor is yours.
Thank you. So thank you very much, Amel, for the, I would say, very generous introduction.
Mm-hmm.
And thank you for the invitation. I'm very excited to be talking to the group, given the focus of the research group and the topic. It's been research in this group. I expect to share some of the work that we've been doing, which I hope it's relevant for the work you're doing, and I'm very much happy to take any question as we go forward. It's the tone of my voice okay? Can you hear me okay? Okay. So I titled my talk Engineering Trustworthy AI System, right? So it's really about those systems in which we have AI components and we have the constraints of trustworthiness, which it's building trust is, you may say it's actually a philosophical concept. It's very hard to engineer trust in the systems, but there are some commonly agreed properties that we need to enforce in systems to ensure this trustworthiness. So before I dive more in details in my talk, hopefully I can make this work. Okay. So what we aim to do in my group is to achieve what you see at the tip of the iceberg, the build trustworthy, reliable system, and be able to maintain this property throughout the evolution of the systems. As you can see from this picture, there is a lot of challenges and the needs that we need to unlock if we want to achieve this level of trustworthiness. There are a lot of issues related to data, which haven't been traditionally the main focus of software engineering activity, but in the case of AI-based system, it's in particular the type of AI that is successful nowadays, machine learning. Most of the behavior that we emulate in the systems derive from the data. So data, it's very important asset. It's a first-class entity that we need to engineer properly. And engineering data comes with a different set of challenges. Here in the picture, I pointed just a few challenges around the imbalancing, the shifting, and the noise that you can have in the data. And then there's all the modeling issues, right? So there's so many different ways you can actually try to infer this knowledge from the data. And one of the tricky thing in learning in the sense of machine learning is that usually often we can end up with a model which may actually be very underspecified. So we can have a model that is not the best we could have. And that's not the goal if we want to engineer a trustworthy system. So we need to have mechanisms in place that allow us to improve the quality of the model. So the health of the model is also very critical. And of course, to achieve this, we have to instruct the hardware to do the processing for us. So we end up have to write program statement as we are accustomed to doing. And as we do this, we also have to deal with all the issues related to programming. So the scope of issues that we have to tackle when we deal with machine learning BI system, because I think AI is more broader than that. It's broader than what we dealt with traditional system. And this is what my team have been mostly focusing over on the past few years. So this is just to give you an example of the team. So the work I will be presenting, it's in no mean all my merit. It's mostly thanks to this bright minds that I'm lucky to work with over the years. So to engineer trustworthy system, there are a few requirements, right? So we need to move beyond focusing only on the accuracy of the algorithm. It's commonly agreed now you can engineer trust if you can explain the decision logic of your system. So explainability it's something that is fundamental and core. There are issues around fairness, right? So you need to, people trust the system if they feel that they are getting a fair treatment from the system. So fairness is a very important property. Privacy preserving, the system needs to be able to preserve the confidentiality of the information that's been processed through the system. And data is a very important asset. Data holds sensitive information that shouldn't be leaked by no means through the system. So those are important properties, among others, to enforce trustworthiness. Most of the learning approach that we commonly use, in general, rely heavily on correlation between entities and events, right? So, and these correlations are not, system can often make decisions based on spurious correlations or just coincidental association. So causality is something that it's desired, and it's very important if we want to improve the trust in the system that we're building. Of course, the system needs to be robust. So this is not just a few attributes that needs to be enforced if we are to ensure trustworthiness in the system. It's by no means a complete list of attributes, because as I said in the beginning, emulating trust in the systems, the concept of trust is a bit broader than just these few dimensions. But these dimensions, we believe in the community, are essential to pave the way through trustworthiness. So for the context of this talk, I took the case study of autonomous systems, which is a case of systems in which we are heavily in deploying AI components, and which is something that we have been looking in my groups as a very good, interesting case study of application of the work that we'll be doing around engineering AI-based system. So autonomous system, why is it an important case study? There is a lot of expectation on what it can bring to improve the quality of life, right? We expect that this will improve road safety, among other things. It will free us from driving. So in some sense, kind of improve our productivity. It would increase accessibility, because many people will be able to actually move around more autonomously if they could have access to this type of technology. It may reduce costs, it may reduce consumption, and there is the public buying, right? So it's something it's very popular. If you look at this recent survey from McKinsey, there is expectation actually that this technology will be around as close as 2035, right? So there is a hope and high expectation on buying on this technology. But then to reach to that level and to fulfill this expectation, we need to ensure that we're building autonomous systems that are trustworthy, that are at the minimum safe, right? And there is this, I'm sure many people are already familiar with this scale. There are the 6 level of safety of this type of system, and the levels that interest us are the level 4 and 5, right? So level 3, it's the system can run somehow autonomously, but still require the user to be ready to provide input in case there is any issues. Level 4, the system should be able to run autonomously and in a controlled environment. And level 5, it's full autonomy, which is the most challenging part, right? So the system needs to be able to operate in any environment and any conditions. So there is a big hope and a big push toward that feature, and AI is actually leading the way in this approach. So what is a typical autonomous driving system looks like today, right? Just to give a pictorial view of what we're talking about. So I'll be focusing mostly on the perception part of it, and the perception part is actually driven by a combination of camera, radar, and lidar. So we recording the surrounding, we're estimating the velocity of things coming around, we're estimating the depth of things. So this work by collecting information using this different type of technology that are positioned around the car. And this information is mostly processed nowadays, for many of those suppliers through neural networks. So the information is collected, it is integrated in sort of point clouds, and then we're using neural network to actually process the information and provide a signal to the vehicle in almost near real time, so that we can actually provide a sense of everything happening around the vehicle so that it can navigate the environment. So you see neural network at the core of this technology, at least for the most successful one that we are seeing on the road today, like a Waymo or the others, just to name a few. And this information fuse allowed the technology to navigate. But as you can see, this car in general is navigating in very unstructured environment, right? Which means there is a lot of issue related to the quality of the data. And also in a typical autonomous driving system, you have more than one model that is interacting. So you have multiple models processing information and sharing information among them, right? So you even have feedback loops in this system. So the system is way more complex than just processing one machine learning model. So ensuring that this system is reliable requires to be able to ensure the reliability of all the models, all the components that compose the perception, at least in this case, the perception of the systems, right? And there's a lot of data that being processed in real time. So a single autonomous driving car, in a year, it's generate more information than millions of money to use on Twitter, just to give you an idea of the scope, of the scale of what we're talking about. And this is a pictorial view of what's the architecture of these autonomous driving systems. And in my talk, I'll focus more on the perception layers, localization, perception planning, and drive-by-wire. But it's actually a very complex system in practice. So ensuring the safety and auditability of these components is challenging, right? So if you look on the left side of my talk, of my slide, for traditional system, usually we had the code. So we had a set of statements that we will instruct the machine to produce the behavior, and usually we have a fairly more simpler way of testing for the behavior of this. So we have the specification. In some cases, we have Oracle, we have near Oracle, and then we do unique integration and system monitoring as it's running. But in the case of machine learning-based system, we have this additional complexity that comes with data, right? So we need to have mechanism to deal with data quality, right? We need to monitor for concept drift in this data as the system is evolving. We also have the infrastructure that is used to serve that needs to be assessed for reliability. So we have unit tests, we have integration tests. We also have the model, which is a third class. We need to be able to test for the behavior of the model. As I pointed out in the beginning of my talk, it's very easy to build on the specified models. I'm sure most of you have been aware of the paper from the Google team, which actually, I think it's from Damour a few years ago. They were reporting about their experience at Google of building machine learning model. Despite all the best practices that they had in place, the odds of building on the specified model was actually very high, right? So it's actually very challenging to get this right. And once we have this and we deploy the models, because there is strike dependency with the data and the evolution of natural, if the data is non-stationary, so the data would probably decay over time, monitoring and updating and maintaining the systems valid over time is also something very challenging. So system monitoring, data monitoring, and prediction monitoring is something that's very important to keep these systems healthy. To ensure the auditability of the systems, we need to be able to explain the decision logic of the systems, right? So as you all know, the high capacity learners that we mostly rely on nowadays are, for a majority part of them, black boxes, right? So it's actually very hard to provide reliable and trustworthy explanation of what those models do, right? So this is just to convince you. If you look at this two examples, they are very popular in the literature nowadays. The first one is the case where we're using saliency mapping. So we're using activation pattern of the neural network to make sense of what the model's attention is focusing when making the decision. But as you can see from this example, this is something that is not fully trustworthy, right? So in the first cases, we have a trained and untrained models that seems to be displaying pretty similar pattern of activation when making a decision about the birds. On the second example, you have the case of a model that is actually making very different decisions by similarly focusing on the same area in the picture, right? So these tools, they are not totally useless, but the quality of the technology at this point, it's not fully trustworthy. So there is another set of approach that is usually used, the post-hoc techniques, to try to mimic the behavior of the complex system that we can't explain, to try to make sense of how the decision unfolds, right? So those attribution-based techniques, I'm sure everyone is more familiar with LIME and SHARP. They are heavily used, even in the industry, to try to provide explanation about the behavior of models. But these techniques are also not fully trustworthy, right? So in a recent study that we did a few years back, we actually explored how the consistency of different techniques on the similar problems. And what you observe is that often they can even provide very conflicting explanations about what the model is doing. And this is the root cause of this problem stems from the fact that they rely on specific sampling mechanism in general. So they are local explanation techniques which generate explanation that heavily they depend on how you actually sample around the region where you wanted to explain, right? So the mechanism used to guess the behavior of the model is not something that is currently fully trustworthy. Even worse, last year we published a paper at iClear where we actually show that you can actually manipulate the explanation that you generate, and there is no way to prevent this manipulation. So we formally proved that you can obfuscate. For example, in this case study, we had a model which was biased, obviously, because the decision was heavily depending on the gender. But we could generate explanation that is where minimizing the impact of that specific feature on the decision of the model, just by engineering the way we sample. Yes, Amen.
A quick question, actually, because in the first part you said it's not reliable, and this one is untrustworthy. Is it a consistency? How would you define that reliability or trustworthiness for those systems?
You mean the explanations?
No, it's kind of the explanation, for example, when do you say that they are reliable?
The techniques used to try to explain the system is what is not reliable, fully reliable.
Okay.
Which means the explanation that you get out of it is not something that is fully trustworthy, that you can actually trust, because you can manipulate explanations. So the process of explaining the systems can be engineered in a way that provide an explanation that is desired, that is chosen upfront. That's what we actually show in this paper. In this paper, we had a bias model, and we were in the setting in which the model will be audited, right? So you wouldn't want the model to be audited and be classified as a biased model. But of course, to explain how the decision of the models unfold, you need to generate explanation to explain how the models works. So we generate the first explanation. As you could see, in that explanation, the gender was actually a very important dimension in the decision logic of the model. And using the exact same technique, we just adjust the way we were sampling around the area in which we wanted to explain the given decisions. We could actually generate explanations that minimize, that actually obfuscated the contribution of the gender dimensions. And if you're auditing my explanations, unless you have full access to the whole process and you also try to generate multiple variants of explanations, it's very hard to actually identify the issue. So post hoc, the point I'm trying to make is that post hoc approach, attribution-based, will actually don't have access to the inner working of the model, but just sampling around the manifold and try to learn a more simpler interpretable model based on the decisions observed of the models. They cannot provide a full picture of what the model is doing. Of course, if they could, we didn't need a complex model in the first place, right?
Yeah.
In any case, right? So, but that's the thing. The problem with those techniques is that they are very popular and they are being widely adopted. But the case we're trying to make here is that you can generate adversarials for those techniques, right? You can always, in any explanation, I can generate another explanations that does what I want it to do, that shows what I want it to show about the models. And this is a big pitfall because if I'm subject to audits, I can actually manipulate the artifacts of my audit. Yes, there is another question. Navi.
Hi. Yeah, thank you for raising this point. I just also have a quick question here. So, are we talking about only sharp here or any other explainability techniques?
So in the paper, it was sharp.
Right. So,
But the attribution-based techniques, they all work on the similar mechanisms, right? You sample around those local explanation techniques. You sample and then you observe the behavior and then you try to.
so did you? I mean, in like maybe in the future work or probably in the same work, did you explore any other techniques or like experimented and also validated this? Yeah. So this drawback of sharp on any other technique as well.
So in the paper, we experiment heavily around sharp, but I think the result will apply to attribution-based techniques
Right.
in general,
Okay.
and local explanation attribution-based techniques, because
Right.
the flow we exploit, it's a characteristic that is common to that family of techniques, actually.
Right. Okay. Thank you. Thank you so much.
Yeah. And the key point here is we are not there yet in terms of generating trustworthy explanation for high capacity models. Like if you have a model that is not interpretable by design and you're just trying to mimic the behavior of the model and guess what the model is doing by sampling extensively, there is a risk, there are limits around what the full picture that you get from the model using those approaches, at least for the techniques that are commonly used nowadays. And I think they are more like, for example, last year, they have been more work trying to generate different ways of explaining the behavior of models that doesn't necessarily rely heavily on how you sample around the instances that you want to explain. Because the main problem comes from that side, at least in this case. Good. Any other questions? So they can't be manipulated. That's the key point I wanted to make here. Okay, so which is a challenge. So at this point, another, I think, very popular aspect of or limitations of high capacity model is the fact that in general, they are not very robust, right? So there have been a lot of work to try to improve their robustness, to assess the level of robustness of those models, but this is a common problem that we had to cope with, right? So this is also a very popular example. I think we have, is it a question in the chat? This is a very popular example of how slight alterations on the images could actually significantly change the decision of the model. In this case, the model is confusing a stop sign with a speed limit sign, which is quite critical in terms of the context of autonomous driving, for example. This is another example that is also very popular, which is a case of lack of generalization, right? So I think maybe you may have spotted this. This is the typical case of Pablo distribution. So the model was trained on instances in which this specific input almost certainly never occur. So as the model is trying to make sense to actually guide the decisions, the model is unsure of how to classify these specific instances, right? So generalizing out of distribution is a very difficult problem because usually when we build the model, we make assumptions about the distributions of the input data, and the model is trained with the hope of generalizing, but in general, there is a limit of how far the model can generalize. And understanding the operation domain of the model is very critical to ensure that appropriate control I put around the model when the model is integrated in the systems. So So at this point, you maybe wonder if it's actually possible to provide safety guarantee to reach level 4 and level 5, right? Given all these shortcomings and these pitfalls that we're currently facing, and that are inherent to the nature of the models or the learning mechanism that we're using to build the systems. And I don't have a clear answer to this, but I think extensive testing definitely help, right? Which is what we have been mostly investing and trying to contribute on, right? So I think having efficient techniques and efficient tools that allow to obtain a full picture of the behavior of the model is critical to ensure that the models are used in an appropriate context, in the right operation domains, and that we can actually build a system that's as robust, at least reliable, that we could explain to some extent, and that's at some point could be considered trustworthy. So when we build the models, just to put the tables before the techniques that I will present later, these are the typical steps that you have to go through, right? So in general, you have to train the model. So it means you train the model in a specific environment, in a specific context, which is something that you have to configure in general. And then there's the data. The data comes from different sources. You could load it from a disk. You could just access it through an API. You could get it from different sources. In the case of autonomous driving, we've seen that we're collecting a lot of data from different sensors. And then we have to fuse these data usually. In the case of autonomous driving, just this point cloud alignment problem is actually considered a difficult problem because usually you get ghost points when we're trying to fuse the data. So it's actually challenging to get the data right. Once you have this data, in general, before you can learn from the data, you have to apply some processing on the data. Once you do this, then you have to decide how you want to learn from the data, right? So there is the architecture that you have to design, what kind of network, if you want to use neural networks, how many layers. And then there is all these hyperparameters that you have to choose. What is the learning rates that is adequate? What is the batch size, and so on. Then activation function. How do I process these informations? How do I assess the loss? How do I penalize the contribution of each part of different parts? How do I optimize? So the configuration space can be pretty large, right? And once you have made a decision, you can actually start training the model. Typically, usually you do backpropagation to then keep updating your weights until you get something that you can use, right? So you have a model, then you can assess the model, and using hyperparameter, you can fine-tune the models. But you select the best model among the set of candidate models that you get through this fine-tuning process, and then you get the models that you can actually use, right? And in general, before deploying the model, you also have to do sometimes some post-processing. For example, if there were biases identifying the model, you can apply some post-processing techniques to mitigate some of those issues. And then you can have a model ready for production. But the whole point I'm trying to make here is that there is a sequence of steps that you have to go through in which important decisions are made. And each of these decisions have an impact on the quality of the model that you end up getting ready for deployment. So if I were to compare the space of faults, like where things can go wrong for traditional models, for traditional systems in comparison with machine learning-based systems, we can see from this brief picture review that it's actually way broader, right? So in the case of machine learning models, you have a lot of modeling issues that you have to ensure to get right. You have a lot of data issues, and then you also have implementations issues. So how do you navigate this space to get things right? And more tricky is that finding bugs in machine learning programs, sometimes it's actually very hard compared to traditional systems, right? So this is a brief statistic from the literature showing that in general, 80 to 90% of the time is spent debugging and tuning when you're actually building the model. So you spend a lot of time and energy to try to get it right. So figuring the initial math is not actually where most of the efforts goes, right? So we really need to provide support in the debugging and fine-tuning phases. And what is fine-tuning, finding bugs in those systems hard? Well, it's hard because some of those bugs, the majority actually in general, can be very invisible, right? So for example, if I were to ask you in this specific example, where is the root cause? of the bug, because there is a bug actually impacting, if you look at the erratic behavior of the training errors. So there is a problem in the modeling. And turn out the problem here can just come from the non-determinism of the globe function. So the labels are going all over the places. So finding this type of errors in system can be actually very, very, very difficult. So the stochastic nature of things that we're dealing with makes things actually very difficult. Another issue is that this model are very sensitive usually to the hyperparameters. So the difference, just picking the right learning rate can make the difference, right? Having the wrong learning rates can actually lead you to a very poorly performing models in comparison to a state-of-the-art models. Right? So finding these small naps across the different EPO is something that is very, very tricky. So this is another example of bugs. This is actually from a real sample collected from the literature, where you can see here there is a design issues, right? So instead of using for the binary cross entropy here, the appropriate solution would have been a categorical cross entropy. But all those small differences and errors actually make a very big difference on the performance of the result down the road. So you end up here with a model that have long training times and a low accuracy because of this design issue in the development of the model. So it's important to have techniques to actually help identify this issue early on in the process to ensure that we improve the quality of the overreaching model. So to assess, to help in this regard, one of the things that we propose is we brought program analysis to the problems, right? Because if you remember all the steps that I presented for building the models, we are generating a set of statements. So it is a program. It is a program that have design issues. It is a program that have programming errors. So we can actually analyze the program and identify some of the errors. So that's a static structural errors. So in this work, we propose a linter for deep learning programs, right? The benefit of this approach is that we don't need to actually train. So we don't need to run the training program, which means we can catch error early on in the process. So it saves the work cost, it's less expensive, and it's actually very fast, right? So the assessment of this, of the technique proposed in this paper, you can check in the literature, shows that we achieve 91% accuracy on this type of errors. Of course, the limitation here is that everything that is related to the interaction with the data, we can't detect at this stage, because we can observe those type of issue only when we start running the program, right? But at this stage, with a static-based analysis, we can already support the extraction. So there is a tool that you can try, actually. It's open source. And it's been around for some time now. So how does it work? So how did we build a technique? Well, we did program analysis. So we leveraged a taxonomy of common defaults. So we're using a taxonomy of faults that currently occur in those programs, we can actually specify detection rules. We also build meta models for deep learning programs, which actually capture the structure that we expect from the programs. And using these two ingredients, we could actually build a tool that allows for graph-based verifications. So how did we identify common faults? We followed the common approach. We explore programs that were built using this. At the time, these were the most popular libraries that you could use for building deep learning program. We had PyTorch, and of course, TensorFlow and Keras. And we scroll this open source data repositories and model repository GitHub and Stack Overflow to extract this artifact. And when we extracted the artifacts, we use an open coding approach to actually process the artifacts and extract description of bugs that were specific to deep learning. So in the whole process, everything that was generic was discarded, and we only focus on the issues that were deep learning specific, that were related to the decision logic of a deep learning model. And based on those information, we actually design rules. We specify a rule for detecting. For example, you can reshape data retention. We design the detection rules, unnecessary activation removals, zero gradient reset. So there is a set of commonly known problems that occur frequently in those programs that we analyze, for which we specify rules. And then once we have this, we specify detection rules, and we leverage graph transformation, which in that case was pretty fast to detect the problem. So the flow of neural lanes, it's pretty straightforward. So from a program, we use our meta model to generate a representation of the program. And on this representational program, we apply an approach similar to what have been done for design pattern detection in the past. Once we have specified the issues that we're looking in the program, we use graph transformation to detect for the occurrences of those issues in the program. And as the program runs, we will provide a list of violations that it's provided as feedback to the users to fix the issues. We have been working on extending this to also suggest some fixes for some of those, because for some of the issues, the fix sometimes it's actually pretty straightforward and could be recommended to the user of the tool. So this gives you a picture review on the different steps. So it's a tool that have shown to be very effective. So we have been assessing it both on synthetic and real systems that we could collect. And it's actually very efficient. Whenever we detect the errors, the average response time was between seconds. In second amount of seconds, we could detect the issues. And we could detect most of the issue, including issues not reported on the platform. Right? So it's actually a very efficient ways of solving the problem. But of course, as I presented earlier, we can only capture things that are limited to errors in the structure of the program. So every issue that's manifests through the interaction of the data through the training process, like for example, a vanishing gradient, we couldn't detect at that stage, which is why we actually also apply dynamic analysis approach to detect issues during the training process, right? So we wanted to capture defects that occur as we training the programs. Of course, this is more expensive than the previous approach, but it's still less expensive than testing the resulting models, because once we test the resulting models, well, we don't have a route back to fixing the issues unless we restart the whole training process, which is usually what is done to regularize the models. There is some overheads, but the good thing we observe is that usually during the detection process, the issues are detected early on during the execution. So just after a couple of epochs, we could already get enough information to make a diagnostic about what is going wrong in the training process, instead of running all the execution, the training, and detecting that there is a problem at the end of the process. So this approach, it's actually happened to be a bit similar to what SageMaker of AWS is proposing. So in the context of the paper, we were actually asked to compare to this approach. And these property-based testing techniques happen to be actually more effective than the AWS SageMaker. But the good thing here is that it's a property-based technique, so it's open for expansion. So you can specify a new property that you're interested in monitoring and detecting during the training process, and you could be uncovering additional issues during the training process of the model. So the tool is also available. And just to give you a broad view, yes, Amen.
One more question.
Yes.
In the three axes you showed, the data problems, and there was like correctness in each of them.
Yeah.
I guess those techniques, address some defects in that matrices, right?
Yeah.
So is it that these are the most common problems, or are they the easiest to spot? Are they kind of problems that are usually avoided by best practices, or what kind of that space is covered really?
So in the literature, you have techniques that are proposed for data issues generally. And some of those techniques even leverage the logic of the training process to spot issue in the data. So there is some interactions between the two. And then there are techniques similar to those that I'm presenting currently that are focused on model issues. And of course, detecting model issues also interact. There is this interactions and interference with issues in the data. And of course, if there is a bug in the implementation, of course, this is also impacting what we can achieve as the modeling level. The current techniques are still not sufficient for detecting all the issues. From what I know in the literature, you can detect some,
Yeah.
But again, another tricky thing is that when you're modeling, usually the design decision that you make often depend on the characteristic of the data, right? The dimension of the data and so on. So we don't have good techniques currently to allow for tracing across these 3 different dimensions. So most I've seen have been done in silos. So there's some stuff done for data that you can do early on in the process before you start training. There are stuff that allow you to spot issues as you're training. You can use traditional debugging techniques to test for the implementation of your code, although the practices, like there are some studies that we have done looking at open source machine learning model project in practice. The reality is that in general, those problems are deficient in proper software testing approach, which means the implementation that is done to generate the model and put the model in production, it's not tested well as well. So that we still have a lot of blind spots across these different dimensions.
This is yeah, because of the cross dependencies.
Yeah.
I guess there is also a kind of, there might be a richer notion of what is correct or what constitutes an issue. You know, it might be that you have high accuracy, but by debiasing you decrease accuracy.
Of course, right? So there have been a big focus early on usually it was the accuracy, anti-robustness becomes first class, and then biases, fairness become another first class. Now there is also the confidentiality of information, right? So models leaks, they memorize informations, right? So if you want to minimize these information memorization problems, in general, it comes at the penalty on the accuracy of the model. So there is tensions across these different properties when you try to enforce trustworthiness. And currently, there's no established best practice where to put the cursor, right? Like, for example, when you train the models, you try to get the optimal model, but conceptually, we know that in the Rashomon set, you always have a set of multiple equivalent models, right? As you test on the test set, you have a family of models that can display similar performance on the different criteria. So searching the space of model for finding the ones that satisfy much of your criteria, it's not as far as I know, it's not a common practice because also it's very expensive to do that. And there are so many possible alternatives in general. So what people will do is that, you know, when you get the first good candidate, then you will try to refine based on that direction to increase the properties that you're interested in. For example, if there is a biases, you will have to try to mitigate using either the post-debiasing techniques or reworking the data to work around the root causes of the bias to increase the fairness of the model. If the model is memorizing, you will try to understand what kind of information the model is memorizing, which means it's not generalizing enough on those. Then there are mechanisms that you can put in place to try to minimize these memorization issues and try to improve the performance of the model. There is no clear recipe that allow you to navigate these different dimensions as far as I know.
Yeah.
I don't know if that answers your question.
Yeah. Thank you.
And even if you look at large language model nowadays, the way they are trained, they actually usually train in sequence, right? So they are trained on different tasks and at different steps. So a first model is trained using pretty much everything you can get. So data quality at that stage usually is not considered a big problem because the architecture, the model is so complex that you need data just to be able to converge to something. And then once you have a good first candidate, then you start worrying about the tasks, the downstream tasks for which you actually train the model. Then you fine-tune the model with better quality data. So usually data quality curation comes a bit late in the process. And then it's used to fine-tune the models, and it gives you a model that is better for that specific task. And then you start looking at other dimensions. Is it robust? Is it biased? And so on. So there are different methodologies that are followed. There is no established best practice as far as I know at that point.
Yeah.
But the point with the work that we're trying to do is actually to provide you the tool to get the information right about what the model is doing, regardless of the methodology that you're trying to follow, so that at least you can make informed decisions, right, about how you want to go forward with your model. If it's ready for deployment, how do you need to control it in production, and so on.
Okay, thank you.
Good. Okay. Sorry. Okay, so this is an example of the type of issues that we implemented in our property-based approach. So we could detect issues related on trained parameters. For example, if you had a poor weight initialization, this could be detected as you start training the models, and then you could get a signal about it. If you had a neuron saturation, you could detect these issues. If your activation goes out of ranges, we can actually detect this fairly easily. We also have optimization related issues. So if you have, for example, a diverging loss, so the approach could allow you to detect this. If your loss was fluctuating, so you could detect this information. So we build the approach based on commonly known properties that have been specified as properties that should ideally be satisfied during the training process, right? To ensure that you're learning, you're making progress through the learning process, you're optimizing properly, and so on. But again, it's not comprehensive, so it can be expanded to cover more issues. And the way the approach works is that we just monitor the training process to extract information. So there is this overhead that comes with this instrumentation of the training process. And once we have the informations, based on the information and the specifications of the properties that we're interested in testing, the approach, the tool that we have put online, perform some verifications to actually provide a signals about the behavior of the training process and progressing. So this is the techniques that have gained some interest. We were actually invited to demo this at Meta at some point. So it can be useful because training is expensive. In general, you want to know early on in the process if you're doing wrong, right? So we apply this in concrete real case studies, and you can actually detect issues early on, significant issues. And you can detect more than SageMaker, but this was done because somehow TOSEM needed this evaluation to accept the paper back in the day. So it's not meant to comparison with SageMaker, but it can actually detect. And SageMaker also can detect some of the issues that we are detecting with the tool. Okay, so I encourage you to try it if you're interested in this type of problems, and if you find any issue or any, just share the information with us. We are very much happy to continue to improve this. So if I just take a step back, the first technique I presented was meant to allow for testing and verification on the training program. So you didn't train, you just had the scripted program, you can detect errors in the program. During the training, you could detect additional errors. What happened is that once you finish this process, you get a models. That model itself as well, it's likely may not be robust. You may want to know what's the robustness level of that models. And you may want to know what is the operation domain of that model, right? And to do that, you need to be equipped with techniques to do this. So we proposed back in the day, deep evolution was a search-based approach, right? So the goal of the approach was to have a brilliant mechanism that allow you to exercise the decision logic of your model to detect cases where the behavior of the model deviate from what you expect, right? Of course, we don't have an oracle in this case. So what we did is we leveraged metamorphic relations, right? So we had a set of test data, initial set of test data, and leveraging metamorphic properties on our data set, we expanded this test data to generate additional test input that could uncover issues in the behavior of the model, right? And we use search-based technique to search for transformation. So we were searching for operations that we could apply on the input data to generate additional input data that would be relevant for our testing scenario. Does that make sense? So the whole idea of the approach is we have test cases, we have our DNN on the test. We use the DNN, so we exercise the decision logic of the DNN. We have an adequacy criteria. In our cases, we experiment with different criteria. The early version were with neuron coverage. So yes, Navid, there is a question. You're mute.
Sorry. Yeah, what kind of transformation did you apply?
So, for example, in the case of images, the metamorphic transformation, for example, I can just change the contrast. The semantic of the image should not change, right? I can change the background. If I have an image, let's say, of dogs and cats in the sunny days, I can put it on the cold ice as we have in Montreal. the semantic of the image should not change, right? The entity identifying the image should still be dogs and cats, right?
Because
So
basic
yes.
Transformations are already covered, in some cases by using like image augmentation during pre-training, right?
So this is the thing. When we look for transformation that maximize the odds of uncovering a behavior that is not that a normal behavior of the models, right? And when we find those transformations, we use them to generate additional test data. And this data set is actually used for retraining the model. So we can regularize the model by retraining, providing more knowledge about areas in which the model is weak. And this way it's improved the robustness of the model. So the approach actually proven to be working pretty well. In case of images, for example, it works very well. We have applied this on 3 modality: image, text, and sound. Yeah.
Right. And what would be the normal behavior of the model here? Like, is it just...
So for example, if you have a model that is identifying the content of entities in an image,
yeah.
So if you give an image of a cat, the model should say this is a cat, right?
Right.
So if I change the background from, let's say, a lake to a snow, and the model says this is a wolf, then there is an error in the behavior of the model.
Right.
Because we know that it should be a cat, right? We don't have an oracle, but because we have label data, we can use the label data to generate additional test data.
Yeah, exactly. So that's one point. So in this case, the requirement is the label data.
It's the label data. We have label data that is used to test the model. So here we're testing for robustness. So the model is already trained, right? We already have a model that have been tested, right? You have validated, you have tested the model, so you're happy with your model. At that point, we want to know what is the operation domain of this model, right? For that, we test for robustness. How far we can improve the robustness of the model, and where the model is, what are the issues with the model? Okay. So we use search base to search for the transformations.
Yeah, but I mean, so if there could be infinite number of transformations.
Of course, that's the problem. Not all transformations are good, right? And finding good transformation is actually a very challenging problem, right? So depending on the type of entities you're dealing with, searching for metamorphic relation, it's actually a difficult problem, right? For some problems, it's more easier. Like if you're dealing with image, they are very natural transformations that you can apply on images. But if you're dealing with a different entity, like for example, in text, there are also now metamorphic transformation that you can apply on text, but it's less obvious than, for example, on images. Okay. But for us, the good thing of our approach is that we build on a base set of transformations, and we use the search process to evolve this combination of transformation. So we want to transform further and further by combining semantic preserving transformations. So that's the whole idea. Of course, when we do this, we have to control for the quality of the image. For example, if I blur an image to the point that there is nothing visible in the image, then this is not a valid test input data in any case, right? Because it's not useful. There's nothing to see more in the data, and then if the model is expected to fail on this. The fact that the model fails doesn't provide any meaningful signal.
Yeah, but I mean, so by visually inspecting, this could be quite obvious, but like, for a machine, like, how would we kind of...
So we use the system, right? There are some metrics that's commonly used to assess the semantic variability of the images. So we use that to cap a threshold. I'll get to that actually. Okay. So from initial test data, our goal here is to really search for transformations, right? And we got the search with the neural coverage. We want to activate as many neurons as possible during the search process, right? Because our assumption is that if we have observed the decision of the model when all the neurons are activated, then our confidence in the trustworthiness of the model should increase, right? Because we have seen the model in action, and as we were observing the model in action, we were satisfied by the reaction of the model, right? So we want to activate as many. So that's why it's one of the criteria that we're using for the search, right? And then we use 2 types of coverage. We use local and global coverage, right? So we want to maximize the coverage every time we search, but we also consider what was covered in the previous iterations, right? So we want to make sure we're making progress as covering more and more part of the model. So those are the details are in the paper for those. And just to give you an idea, so this come back to your question. So this is, for example, an initial set of transformation that we start from, right? brightness, contrast, pixel perturbation, blurriness, translation, scaling, shearing, rotation. So you can apply all this to an image. It should not alter the semantic of the image. Okay. So from this transformations, we search for combination of transformations, right? By trying to push the models to the edge as we're conducting the search. And then we need to make sure that we preserve the semantics. So that's why we use the SSIM, the SSIM, between the mutated and the original to ensure that the difference remain within an acceptable threshold. So they are commonly acceptable threshold in the literature that we use to cap our transformation. So we won't transform an image too much, but just up to a point that the image normally is still viable and as such. Okay. So this process went on. Yes, Amel.
Futsi, just kind of a heads up that we have only 2 minutes left.
Oh, okay. I need to go fast. Okay, sorry. So we apply this, and this is the fitness functions that we apply, and then this is the transformations, right? So we examine this technique with different evolutionary based approaches, and the results shows that we can actually detect errors in the model. So we can detect when the robustness of the model is altered. And we compared this with existing techniques, actually. And we could detect errors introduced during the quantization of the model. So another set of approach that we propose, I will just go quick fast here, the details in the paper. It's an approach to detect error from quantization. So usually when you have the models, to deploy the models on low resource constraints environments, we usually have to compress the model. And as we compress the model, we alter something, we lose in precision of the model. But in some cases, we want to preserve, sometimes we end up with a more robust model. Right? So we need a technique to detect cases where the quantization process induces errors in the resulting models. And here we use differential testing. So the whole idea here is to search for transformations that maximize differences in behavior between the original model and the quantized model. Very similar in process to the previous approach. So we apply search-based approach to detect this difference-inducing inputs. So we search for those inputs using metamorphic relations as well in these cases. And we have a fitness functions that in these cases was domain-driven and then maximize the differences between the two. So this gives you an idea of the metamorphic relations. And then here you can see the distortion that we apply on images, right? So you can apply different transformations on the images. The goal here is to maximize the differences between the original model and the quantized model. So by exercising these differences, we could actually detect test input data that we can use actually for testing the compressed model. Okay. So this is very similar to the previous approach, but it's applied to detect quantization inducing issues. So we apply this on different data sets, and you could actually find that you can actually automatically find errors that are introduced during the transformation process with a systematic and automatic tools. Okay. Sorry that I have to go quickly on this part. Yeah. So we have the case I'm trying to make is that we need automated quality assurance techniques to support the engineering of trustworthy machine learning system. And we can build technique across all the stages of the development process, right? From the specifications, from the instruction of the training process, we can detect issues during the training process. We can detect issues every time we apply a transformations to the model, for example, from a original model to a quantization model, which is a smaller version of the models. We also propose technique in the cases where instead of neural network, we could use, for example, deep reinforcement learning, which are other settings, which also generate errors potential errors when we train the models. We also propose framework for mutation testing to allow for automatic testing of these models during the training process. And I don't have much time to hide. Do I have or not? I don't.
No, thank you first.
Okay. I'll stop here. Yeah, I will take any more questions. I had more material, but I think I will stop here.
Okay, thank you very much, Futsi. A big clap.
Thank you for having me.
I don't know whether you have time just to kind of give the chance for those who are rushing for another meeting or so to go, but I don't know whether you are able to stay a little bit longer.
Yeah, I can stay longer actually.
Okay, perfect. So this way we will take also questions.
Yeah.
So those who have to leave may leave, but then for others, we can ask more questions and have further discussions. So I don't know whether someone want to ask question. I have one.
Yes, please.
Okay.
There is Radu as well.
Radu, go ahead.
I thank you for it's a very interesting presentation, and you've covered so much in terms of testing deep learning models. It's really impressive. I wanted to ask maybe a couple of things. One is, in my testing of such models, I'm typically interested in particular types of errors that are driven kind of by the risk of that having those problems in place could appear in a real deployment of these models. Is there any work on sort of directing the testing in particular areas of usage of ML models?
So they are testing. They are work that look at testing for safety, for example, based on some safety criteria. They try to use the system as a black box. I think Lionel teams have been doing a lot of work around the topic. So based on specification of cases that's characterized as high hazard risk for the systems, you can use that information to drive the search for test inputs that are likely to uncover cases where the model is likely to fall into those cases. So there have been work from I know some from Lionel Briand team where they actually use this safety specifications. So they will characterize hazard risk of the systems, and then they will actually look for test cases that could help uncover, ensure that the model will not fall into those specific. So if you have a specific criteria that we are mostly interested in general, with search-based approach, we can actually drive the search for test input data in a way that we maximize the occurrences. We look for cases that maximize the occurrences of those cases, and those will be interesting test case data.
Yeah, I think that those should come from requirements, maybe at system level in a way.
Exactly. We need to know what's exactly, like for example, in the case of differential testing that we had between the original model and the quantized models, our specification was we wanted both to align, right? So based on that, we drive the search for cases where the diverge in behavior. So if we can specify the behavior that we're interested in, then I think we can adapt most of these techniques actually to search for relevant test cases. Yeah. Okay. There is another question, Chen.
Yeah, thank you for your interesting talk. Actually, I'm very interested in the search-based new case generation method. Could you show me again the title of the paper, or just send the title of the paper in the chat?
Oh, sure. I will send I can send the title, all the papers that I can send the slides actually.
By the way, I have a question about this method. How can you guarantee the new generated cases are truly existing in the real world? Because if you generate some images or I don't know that cannot be occur in the real world, so the testing is
totally
not so valuable.
Right, totally agree. That's why that criteria. So for example, we use the SSIM to control for the quality of the images as we transform the images. So we need similar that criteria is very important, right, to guarantee that you control for the realism. There have been some other works where people were actually they had humans assess the images that were generated by this transformation to identify the potential alignment and gaps that we have between what we generate as synthetic images and what's actually realistic images. So that's always an open questions, right? But again, the other counter argument you can make is that, of course, we will probably generate test cases that will uncover issues in scenarios that may not be realistic enough. But in the process, we will generate relevance ones as well, right? So there may be a cost of testing for things that will not happen. But the automatic process, I think, increase the odds that will test for things that are actually very, very likely to happen. Another approach that I've seen is using simulations, right? So in the second part, I actually prepare some stuff on more simulation-based, like software in the loop-based, where you can use a simulator, right, to actually try to control for this. And of course, the question remains, how the fidelity of the simulator to the reality. So we also have this sim to real gap that we have to deal with, but we try to minimize the gap as much as possible. Does that answer your questions?
Yeah, sure. I admit that's a huge challenge. Yeah, we are always trying to minimize this gap. Yeah. Great, thanks.
But it's better to test than to not over test too much because this cost. But it's better to test for cases, including some of few cases that may be artificial, instead of under testing the system. At least my perspective. There is another question.
Yeah, Ginger. I don't know their
Yeah. Thank you for this, for the great talk. I see many very interesting works you have done. Brilliant. I have a very high level question. I think earlier on in your presentation, you mentioned you were asking this question about what kind of safety guarantee we can have for, say, self-driving cars. I quite like this idea of providing guarantees for people, maybe because my background is mainly in verification, and I guess for now, even though we already have a lot of great automated software tools, we still cannot, say, provide some sort of guarantee. Am I right?
This is a discussion that I've been hearing, and I've been in many cycles. And what people say is that even if you remove automatic, just look at driving, right? Cars, right? Also, the safety guarantee that we provide on cars, it's based on accidents, right? So we want the rates of accidents to be below a certain percentage, right? Which, if I remember correctly, in the early days was the normal rates of death of part of the population between 30 and 40, like the most healthy part of the population, right? So we want car to provide to present less risk than what is considered likely to occur in any cases in terms of fatality. So that's why some argument is at least company like Waymo and others will drive in multiple hours, right? So as the cars are operating, they are recording information about how many issues the car has been involved in. And based on this, the hope is that they can make a comparable case between the autonomous driving and the normal non-autonomous drivers, right? So I feel like the guarantees would likely be mostly in that direction instead of providing kind of formal guarantee. I don't think we can provide a formal guarantee that there would not be an accident, right? So I think it's more the odds. It will be something probabilistic. We want to be able to estimate the odds that this accident will occur. And testing, extensive testing definitely help, right? Because it provides this data point that you can use for this estimation. Yeah.
Yes, I think I fully agree your opinion, because I also believe in the end, say after 10 years, 20 years, as the technology evolves, in the end, we can only provide statistical guarantees. We have different types of guarantees, right? Formal guarantee is too much. Is hard. You're probably
measurable, but with the nature of the problem, I think it's hard in that cases. But statistical guarantee is not bad, right? I mean, we already do this for many safety critical contexts.
Yeah. Great. Thank you. Good to know this.
Thank you very much. I can't see extra questions, and we're a little bit over, so let's give another round of applauses to Fritz. Thank you.
Thank you for having me.
For the inspiring discussion. It will be published on YouTube, but feel free to probably follow up as well. And thank you everyone.
Thank you for having me.
Thank you.
Thank you.